Polyhedra. A polyhedron is a solid whose boundary is a union of polygons. We meet polyhedra every day in our lives. Common examples of a polyhedra are cubes, tetrahedra, and prisms. Polyhedra have some nice properties that are not shared by all planar graphs. Most importantly, all their faces have at least 3 agencies, and all their vertices are part of at least 3 agencies. It is also easy to verify that in all polyhedra there must be at least 4 vertices, 4 faces, and 6 agencies. We do not have to worry about loops or multiple agencies in polyhedra either. In geometry, a polyhedron is called regular if it is absolutely symmetric. That is, all its faces have the same number L of agencies, all vertices are contained in the same number D of agencies. D is called the degree of the polyhedron. All agencies have the same length, all angles within the faces are equal, and all angles between the faces are equal. For example, the cube is a regular polyhedron. In combinatorics, we can disregard the conditions on the length of agencies and the size of angles, but we keep the graph theoretical conditions that each face is a cycle with L agencies and each vertex has degree D. One could think about regular polyhedra as three-dimensional generalizations of regular polygons. There is, however, a striking difference between regular polygons and regular polyhedra. Clearly, for all integers n which is greater than or equals to 3, there exists a regular polygon with n vertices, so the number of regular polygons that are different as graphs is infinite. In this section, we will show that this is not true in 3 dimensions. In fact, and our goal in this section will be a proof for this, there are only 5 different regular polyhedra, which is very different from the 2-dimensional situation. One of our main tools improving this result will be Eulers theorems for planar graphs. It is not hard to show that this theorem also holds for polyhedra by showing that polyhedra are essentially planar graphs. Nevertheless, we provide an additional proof for Eulers theorem for polyhedra only. The beauty of this proof lies in its simplicity, as it does not use induction or property of trees. It only requires high school knowledge of geometry. Some of the formulae that we find on the way will be useful on their own. Theorem 12.6. Let P be a convex polyhedron with V vertices, F faces, and E agencies. Then V plus F is equals to E plus 2. Proof. Let P, little p, be a plane that is not perpendicular to any faces of capital P, the convex polyhedron. And let us project P onto P, project P onto P, the convex onto the plane. To get the projected image P prime, as P was a convex polyhedron, the projection of a face with k agencies will be a convex k-gon. Let us count the sum of angles in all the f faces of P prime. The boundary B of P prime is considered a face 2. There are 2 ways to do this, namely we can count by the vertices or by the faces. First, we count by the vertices. Let us say that B is a convex V1 gon, and there are V2 vertices of P whose projected image is inside this V1 gon. Then V1 plus V2 is equal to V. The sum of angles around each of the V2 interior vertices is 360 degrees, so the total sum of these angles is 300 times V2. The boundary of P prime is a convex V1 gon, so its sum of angles is V1 minus 2 times 180. However, the sum of these angles must be counted twice, as each angle is used by 2 different faces of P prime. Therefore, we obtained that the total sum S of angles is S equals to V1 minus 2 times 360 plus 360 times V2, which is equals to capital V minus 2 times 360. On the other hand, we can count the angles by the faces too. If a face of P prime is a convex k-gon, then the sum of its angles is k minus 2 times 180 degrees. Let f1, f2, f3, and so on until capital F be the number of edges of the capital F faces of P. As each edge is contained in exactly two faces, the summations of a little fi summing with index I starting from 1 to capital F, the number of faces, is equals to 2e. Therefore, the sum of the angles in all these faces is certainly S, which is equals to the summations of little fi minus 2 times 180, summing for all index I starting from 1 to capital F, because these are the faces of P. If we take out a constant, it will become 180 times the summations of little fi summing with index I starting from 1 to capital F minus 360f, which is 360 times capital E minus capital F. So if we compare the above formula, that is, the summations of little fi is equals to 2e, and S, which is equals to 360 times E minus F, and S is equals to V minus 2 times 360. Then the proof of our theorem is immediate. So the formula 12.2 is a useful byproduct of this proof. Note that Fi, which is greater than or equals to 3 for all I, for all faces, as the Fi denote the number of edges of various polygons. Therefore, the left-hand side of 12.2 is at least as large as 3f, proving the following corollary. Corollary 12.7, in any convex polyhedron with f faces and e edges, 3f, which is less than or equals to 2e. It is not too difficult to prove a similar relation between the numbers of vertices and edges of a convex polyhedron. Proposition 12.8, in any convex polyhedron with v vertices and e edges, 3v, which is less than or equals to 2e. Proof: let C1, C2, and so on until CV denote the number of edges adjacent to each vertex. As each edge is adjacent to exactly two vertices, the summations of Ci summing with I starting from 1 to V is equals to 2e. As each vertex is contained in at least 3 faces, Ci, which is greater than or equals to 3 for OI, so the left-hand side is at least as large as 3v, which was to be proved. The reader may think that after finding relations between the number of faces and edges as well as the number of vertices and edges, we can probably find a similarly simple relation between the number of vertices and that of faces. This is, however, not so simple. The problem is that in the two previous proofs, we heavily relied on the fact that each edge is contained in exactly two faces and contains exactly two vertices. Faces and vertices do not have such a uniform property. We now have lower bounds on the number of edges in terms of the number of vertices, and also in terms of the number of faces. On the other hand, we have not proved the upper bounds yet. It is plausible to conjecture that such an upper bound should exist in terms of the number of vertices. Indeed, if we have a simple graph on v vertices and keep adding new edges to it, then we eventually reach kv, which is not planar if v is greater than 4. Our task is to figure out how many edges are too many. Lemma 12.9. In any convex polyhedron, E, which is less than or equals to 3v minus 6, and also E is less than or equals to 3f minus 6. Proof. We know from corollary 12.7 that f is less than or equals to 2 times E, then divided by 3. Comparing this to Eulers Theorem, we get E plus 2 is equals to f plus v, which is less than or equals to, now we substitute f with 2e divided by 3, then plus v. After simplification, we know that e divided by 3 is less than or equals to v minus 2. And the claim e, which is less than or equals to 3v minus 6, follows by rearranging. Similarly, proposition 12.8 implies that v is less than or equals to 2e divided by 3. And comparing this to Eulers theorem, e plus 2 is equals to f plus v, which is less than or equals to f plus 2e divided by 3, which means e divided by 3 is less than or equals to f minus 2. And again, the claim e, which is less than or equals to 3f minus 6, follows by rearranging. The attentive reader has probably noticed that the symmetric rule of v and f in our results so far. These two parameters play symmetric roles in Eulers theorem, in lemma 12.9, in corollary 12.7, and in proposition 12.8. Even the proofs concerning these two kinds of results were very similar. There is a deep structural reason for this, and we will explain it shortly. First, however, we are going to use our recent results. We start with a somewhat surprising application. Lemma 12.10. All convex polyhedra have at least one face that has at most 5 edges. Proof. We know from lemma 12.9 that E, which is less than or equals to 3f minus 6. Comparing this to 12.2, we obtain that the summations of little fi with index summing starting from 1 to capital F is equals to 2e, which is less than or equals to 6f minus 12. Therefore, it cannot be that fi is greater than or equals to 6 for all I, as that would imply that the summations of fi summing with index starting from 1 to f is greater than or equals to 6f. It should come no longer as a surprise that there is a similar result for vertices. We could tell the promised deep structural reason for this right now, but we prefer making the reader curious. Lemma 12.11. All convex polyhedron have at least one vertex that is contained in at most 5 edges. Proof. We know from lemma 12.9 that E is less than or equals to 3v minus 6. Comparing this to 12.4, we obtain that the summations of Ci summing with index I starting from 1 to capital V, the number of vertices, is equals to 2e, which is less than or equals to 6v minus 12. Therefore, it cannot be that Ci is greater than or equals to 6 for all I, as that would imply that the summations of Ci summing with I starting from 1 to v is greater than or equals to 6f. Therefore, there is at least one vertex that is contained in at most 5 edges. Lemmas 12.10 and 12.11 are of pivotal importance in our quest for regular polyhedra. They show that in regular polyhedra, the degree d of each vertex can be only one of 3 values, namely 3, 4, or 5, and the same goes for L. That would leave us with only 3 times 3, which is equals to 9 cases to check. The following discussion will simplify that task. Let G be any planar graph, and let us construct a new graph G star as follows. The vertices of G star are the centers of the faces of G. Any interior point would do. Two vertices A and B of G star are connected by k edges if and only if the corresponding faces in G had k edges in common. In this case, each common edge of these two faces will be crossed by one ABH. This sets up a bijection between the vertices of G star and the faces of G, and another bijection between the edges of G star and G. Therefore, if G has E edges, V vertices, and F faces, then G star will also have E edges, but it will have F vertices and V faces. The reader is invited to verify that G star is also planar. See figure 14.30 for an example. Definition: the graph G star defined in the above paragraph is called the dual graph of the planar graph G. The reader should verify that the dual of a convex polyhedron is a convex polyhedron, and the dual of a regular polyhedron is a regular polyhedron. The notion of the dual graph of a planar graph explains the similarity between results on the number of vertices and results on the number of faces. Indeed, if a theorem on parameters V and E is true for polyhedron P, it is also true for the dual P star of P, where these two parameters indicate the number of faces and the number of edges. Now we are ready to find all regular polyhedra. Recall that their degrees must be 3, 4, or 5. Also remember that in a regular polyhedron, all faces have L edges, so the total number of edges is, by 12.2 is E equals to F times L divided by 2. Let us assume first that D is equals to 3. This means that Ci is equals to 3 for all I, which implies by 12.4 that 3V is equals to 2E. Comparing to Eulers Theorem, we get 3F, which equals to E plus 6, which together with the previously assumption by the regular polyhedra, E equals to F times L divided by 2, then we implies that 3F minus 6 is equals to E, which is equals to F L divided by 2. After some manipulation, 6 minus L times F is equals to 12. So all three permitted values of L yield an integer solution to this equation. Now we do some case-by-case analysis. If L is equals to 3, then F is equals to 4. Therefore, E is equals to 3F minus 6, which is equals to 6, and V is equals to 4. There indeed exists a polyhedron with these parameters, namely the tetrahedron. B, the case B, if L is equals to 4, then F is equals to 6. Therefore, E is equals to 3F minus 6, that will be 12, and V is equals to 8. These are the parameters of the cube. Okay, the case if L is equals to 5, then F is equals to 12, therefore E is equals to 3F minus 6, that will be equals to 30, so V is equals to 20. That is, we are looking for a regular polyhedron with 12 faces that are all pentagons. It is easy to see that such a polyhedron indeed exists. It has one pentagonical face at the bottom, one at the top, and to each side of these two faces we attach a new face. This polyhedron is called the dodecahedron. Okay. Now we have discussed the cases where L are different. That is, all faces have L edges, and we have discussed the face which has 3 edges, 4 edges, and 5 edges for all faces. Now we have discussed the second case of degree. If d is equals to 4, then 12.4 yields 4v, which is equals to 2e. Therefore, e is equals to 2f minus 4. Together with 12.7, this implies that 2f minus 4 is equals to f times L divided by 2. That means 4 minus L times f is equals to 8. The only permitted value of L that leads to a positive integer solution is L equals to 3. Then we get f equals to 8, so E is equals to 12, and V is equals to 6. To see that such a polyhedron indeed exists, take the dual of the cube. This polyhedron is called an octahedron. Okay, degree equals to 5 case. If D is equals to 5, then 12.4 yields 5V equals to 2E. Therefore, 3E is equals to 5F minus 10. Comparing this to 12.7, we yield that 5F minus 10 is equals to 3 times F times L divided by 2. That is F times 10 minus 3L is equals to 20. The only permitted value of L that gives a positive integer solution to this equation is L equals to 3. Then F is equals to 20, so E is equals to 30, and V is equals to 12. So our purported polyhedron has 20 triangular faces, 30 degrees, and 12 vertices. To see that such a polyhedron indeed exists, note that we can construct one by taking the dual of the dodecahedron. This polyhedron is called icosahedron, just as the names of other discussed polyhedron referred to the number of faces. This name comes from the Greek word for 20. As we have examined all permitted values of D, we have proved the following theorem. Theorem 12.13. There are 5 regular polyhedra: the tetrahedron, the cube, the dodecahedron, the octahedron, and the icosahedron.